Starting now with definition 29. This should be a definition that you've seen before. Given two sets, A and B, of a ring R, what does the set A times the set B mean? Well, the answer is it's common sense. Depends on how common your sense is. It's the set of things that look like what? Something in A times something in B. Similarly, RB, where R is an element of the ring, is the same as the set R times the set B, which by this definition should mean this. You take R times anything in B, and that's what I mean by RB. All right, definition 30 with respect to groups you've seen before. An epimorphism, a group epimorphism, is a surjective homomorphism. And so a ring epimorphism is a surjective homomorphism. The only difference between groups and rings, remember, homomorphisms, the only difference is that for rings, it has to work both for plus and dot. And of course, for groups, we just have one binary operation. Okay, so now just a way to rewrite a previous definition. We defined what it meant to be an ideal. Remember, an ideal meant that if I took anything, it was closed under dot. In other words, if I took anything in the ring and I multiplied it by anything in I would land back in I. Well, another way to write that, using this right here, is for any R in R, Ri is a subset of I, and IR is a subset of I. Okay, so that's just another way of writing the definition of an ideal in a little different fashion. All right, now let's go to Theorem 32. And Theorem 32 gives us the short criteria for ideals. Now you'll remember we had a short criteria for subgroups, and so this extends that concept because an ideal, remember, is a subring, and if it's a subring, it's got to be a subgroup, right? So here's the short criteria for ideals. And this theorem proves that it works. All right, so what's the short criteria? If you have any subset of a ring R, then it's an ideal if, what do you have to prove? That I is non-empty, and that for any two things, A and B and I, we have A minus B is in I. And then for an ideal, we have this stronger multiplication property that says what? If I pick anything in A and anything in R, if I multiply AR or I multiply RA, I have to land back in I, right? That's criteria for I. All right, so this little theorem proves that this short criteria is enough. Let's go this direction. First off, I claim that if it's an ideal, it automatically satisfies these three things. So I really need to prove only that if it satisfies these three things, it's got to be an ideal. Well, remember that an ideal is a subset of R, so I have all those little properties of associativity and distributivity and stuff like that. That carries over. But if I have 1 and 2, then 1 and 2 is a short criteria for groups. So that's enough to tell me that I plus is a subgroup. And if it's a subgroup, then to show that it is an ideal, all I have to show is that this multiplication works. What multiplication? Exactly what 3 says, right? Okay, so that's a little discussion about why this theorem proves that this short criteria works. And by the way, remark 33, there is a short criteria for subrings, just like there's a short criteria for ideals, and it looks an awful lot the same. if a subset S is a subset of a ring R, then it's a subring if all you have to prove is that it's non-empty, that if you have two things in S, the first subtract the other is in S, and that dot is closed. In other words, that if I take two things from S and I multiply them, I land back in S. The only difference between the short criteria for subrings and the short criteria for ideals is this last multiplication. For ideals, if I take anything in the ideal and multiply it by anything in R, I have to land back in the ideal. For a subring, it's just if I take two things from my subring and multiply it, I have to land back in S. All right. So using that, we're going to prove that this thing is an ideal. Now, what's this thing? Well, you'll recognize the notation for groups. This would be the cyclic subgroup generated by the element A. Well, with respect to rings, though, what we mean by this is it's still called the cyclic ring generated by the element A, but it's no longer taking A and adding it to itself. What this means with respect to rings is it's A times R, where R is anything in big R. Okay, so that's what this notation means, and the claim is that that is an ideal when we have a commutative ring. All right, so let's prove that. Well, we're going to use a short criteria for ideals. And so we've got, since R plus is a group, every group has got the identity, so 0 is in R. And notice I could write 0 as A times 0. We proved that before. So since I've written it as A times something, right? A times anything in R, that's in dagger A, so that's got to be in dagger A. So what have I just shown? That this set is non-empty. Next, what I am going to do is I pick two things from that set, and I need to show the first minus the second is also in there. Well, since A1 and A2 both come from the subring generated by A, there exists an R1 and R2 such that A1 is AR1 and A2 is AR2. Then what? A1 minus A2 is AR1 minus AR2. I can factor out an A because I have the distributive property, and now it looks like A times something in R. That's exactly what the subring generated by A looks like, right? Finally, if I have anything in A, in the subring generated by A, and I pick any R, I want to claim that if I take this and multiply by R, I land back in there. Well, here goes. Well, since A1 is in A, the cyclic subring, right, then there exists an R such that R1 times A times R1 is equal to A1. All right, and then if I look at this R and multiply it by A1, then A1R is, well, A1 is this A1R times R, but that's A times R1 times R, and the point is I've written it as something in A times something in R. That's what it means to be in the cyclic subring generated by A. So there we go. But you recall, with respect to ideals, I also have to prove that RA1 is in my set. Well, the fact that I have a commutative ring tells me dot is abelian, right? And if dot is abelian, once I've shown that A1R is in A, then RA1 has to be in A as well because dot's abelian. So that's got theorem 34. Well, let's plunge on to theorem 35. And you'll notice theorem 35 is similar to a theorem that we had back in groups. Okay, so suppose phi goes from R to R hat is a ring homomorphism. Then if S is any subring of R, phi of S is a subring of R hat. Remember? And if S hat is a subring of R hat, then phi inverse of S hat is going to be a subring of R. We had the same result true for groups. Now we're just going to push it through for rings. So how does the argument go? Well, from our previous study of groups, we already know that phi of S is a subgroup of R hat plus. And phi inverse of S hat is a subgroup of R plus. So the only property left to consider is that closure property under multiplication. So let's look at the multiplicative closure of phi of S. So I pick two things in phi of S. I need to show that when I multiply it, I land back in phi of S. Remember, I'm just showing, I'm proving subring, not ideal. All right, well, since A1 and A2 are in phi of S, there exists an S1 and S2 in big S, such that A1 is phi of S1 and A2 is phi of S2. Then A1 times A2 is phi of S1 times phi of S2 is phi of S1 times S2, where S1 times S2 is an element of S, because S is a subring. So what have I shown? I've shown that A1 times A2 is can be written as phi times something in S. That's exactly what it means for A1 times A2 to be in phi of S. Now, if we look at the multiplicative closure of phi inverse of S hat, again, this proof is going to be similar to the group thing. Choose B1 and B2 and phi inverse of S hat. We need to show that the product is in phi inverse of S hat. How do I show anything is in phi inverse of S hat? The answer is I take this, I hit it with phi, I see if I get an S hat. Well, so I take this and I plug it into phi. Since phi is a ring homomorphism, it's equal to phi of B1 times phi of B2. But remember, B1 and B2 were in phi inverse of S hat. So that means that phi of B1 and phi of B2 are both in S hat. Well, S hat, okay, is a subring so that the product is in S hat as well. And there you have it. I've just shown that phi of this is in S hat, hence it's closed under dot, and that's all I need to show it's a semigroup. All right, time is up, and so I'm going to stop there, and we're going to pick up definition 36 next time.